It should be champagne.
The basic question is the following. So you have a matrix of a rectangular matrix of size n times m, and you assume that the aspect ratio, that n and m will both go to infinity, but they are of the same. They are of the same. Oh, sorry, my tablet. Okay, they are of the same order. Okay, let's try. Yes. Okay. And this will be the known matrix that you would like to recover under some assumption I will mention later on. But the data you have is just that you observe each entry of this matrix independently with probability d over n. Okay, so d, so n is the number of rows, and so d, you can think about that as the average number of observed entries per row. Is that fine? And all the other entries, you don't know what is their value. Okay, and typically you will, for example, assume that P has a simple structure. For example, it has a small rank, and it has what is called spectral incoherence, which you will see what it means later on. So under the assumption that P is simple enough, you would like to observe, recover your matrix P, or at least estimate your matrix P from very few entries of your matrix.
Could I ask you, each entry may be observed with probability d over n. By entry, you mean not element, you mean a row, I think, yeah?
No, the entry.
Entry, but we have n times n.
N times m, yes. So each entry, so there are n times m entry.
Yeah.
And you observe each entry with probability d over n.
Ah, okay. So you can observe several of them.
Yes, yes. You can observe several entries on a given row.
Mm-hmm.
Sure, it will happen. Okay. So the matrix completion. So yeah, I should say that D will be depend on everything will be quantitative, and all the parameters that depend on D and on n. Okay. So I didn't mention, but there is an archive paper, and the result is very quantitative. But as for the talk, you can just think about D, everything going to infinity. But D will stay fixed. But for the record, I will mention some what has been known. So matrix completion problem is, can you reconstruct exactly P thanks to just this observation? So if when P is very simple, as a finite rank, and the eigenvectors are well spread out, this will be possible only if D is at least log n. Okay. So meaning that on each entry, on each row, you observe on average log n entries, right? Okay, the matrix estimation problem is what happens when the matrix completion problem is not feasible. So what you would like to find, instead of reconstructing P exactly, you would like to construct a matrix P, so an estimation of P hat, which is a good approximation of P. And the way, what means good approximation, what people in statistics like, is what is called the mean square error, which is just the sum of the squares of the difference of the entries. Okay. And the best bound that you can get, hope to get for this mean square error is of order mn divided by d. Okay, since there are mn entries, it means that on average, the error you make on a single entry is of order 1 over square root d, right? Okay, because there are mn entries and the sum of the squares. So on average, you make an error of order 1 over square root d. Okay, this of course is possible only with very strong assumption, and P I will mention. So this problem has attracted a lot of attentions, like there are thousands of citations for the papers. It has started with Candace and Tao in 2009, and there are thousands of citations for these papers I mentioned. Okay, so in this talk, I will try to go one step further and to ask a much finer question, which will be the question of matrix detection. Okay, so what I mean by that, I will define it. So if you think about your matrix P in a geometrical way, okay, you will a good way to think about your matrix is to introduce a singular value decomposition. So what is it? That when you have a rectangular matrix, you can you can write it as UDV star, where U and V are orthogonal matrices, and D is a diagonal matrix. Okay, so what does it mean geometrically is that if you take so here my matrix P, here I am in sorry, I'm very bad with here you are in RM, and here you are in Rn. Okay. What I am saying is that the image of the unit ball will be an ellipsoid, and the length of the direction of the ellipsoid are the singular values, are the number on the diagonal matrix, and the direction, the UIs, are called the singular vectors. Here they are the left singular vectors. Okay. And so this is connected to the mean square error because so the mean square error is also called the Frobenius norm, the square of the Frobenius norm, which is the sum of the squares of the entries of the matrix. And the Frobenius norm of a matrix is just the sum of the square of the singular values. Okay, so the matrix detection problem can be formulated this way about which, if you are interested by liking the principal component analysis in statistics, if you are just interested by estimating, for example, the first two singular value of your matrix, what is the critical value of D above which you can reconstruct, you can find a consistent estimator of this singular value. Okay, so this is the first question of matrix detection. A second one would be finding the singular value is interesting, but even more interesting is to have an estimator of these singular vectors, this UK. Okay, so if you fix a threshold gamma, like 0.9, or you would like to know what is the smallest d, such that I can guarantee that with high probability, I can find an estimator, such as a scalar product between my estimator UK and UK, the correct answer is at least gamma. Okay, so all my vectors are units. So this absolute scalar product is just equivalent to thinking about Euclidean distance between U at K and UK. Okay. And the final question would be as the same as for estimating the mean square error, but with a mistake of order. You would like the sum of the square of the mistakes you make, which is of order gamma times the square of the entries of your real matrix. Okay, so this parameter gamma is just that it is a scale invariant. Okay, so you have question about these questions, or is it clear enough? Okay, it should be clear enough.
The last question is unclear. So we like the estimator MSE to be as small as possible, correct?
This number?
Yeah.
Yes. Yes. Sorry. Yeah, you're right. Let's see. Thank you.
Thank you.
Okay, so there are many applications of matrix completion, and the most famous one, which has started all this business, is called collaborative filtering. It's related to what the Netflix price. So collaborative filtering is about a kind of a campaign for making you suggestions of what you would like to buy. And so the Netflix price was, you had the known matrix was as many rows as people registered for Netflix. So, and as many columns as movies, and the entry IJ was just a mark that the user I would give on the movie J. Okay. And so the question was to try to guess what is this unknown matrix P. Note that this matrix is even unknown to the user, because if you don't have seen a movie, you cannot, a priori, you don't know whether or not you will like it. But you may hope anyway to have a good estimator of what is this matrix. Okay. So to make things simple in this talk, I will mention only mostly symmetric matrix. Okay. So my matrix will be square, and towards the end of the talk, I will tell you how you adapt the ideas I've been mentioning on the non-square case, the rectangular case I've been speaking about. So since it's a math conference, I think you will be happy that I don't I will not try to confuse you with too many notations. So I will stick to symmetric matrix. Okay, so now P is a symmetric n by n matrix. Okay. How do you formalize this matrix completion problem? So you have a mask matrix M, where the entries Mij are just 0, 1 Bernoulli variables with parameter d over n, and everything is IID. And you could cook a matrix which is the matrix of observed data, which I would call non-symmetric, by just saying that the entry Aij is Pij, which is the value that you observe, times Mij. So if you don't have observed the value, Aij is 0. And if you have observed the value, Aij just takes the value Pij. And you multiply by n over d here. The result is that the expectation of Aij, since Mij has average d over n, the expectation of Aij is just Pij. Okay. Okay, but this matrix is non-symmetric because your mask matrix as a priori is just IID Bernoulli. Okay, so but you could cook a symmetric matrix, which in some sense has more information by just taking A plus A star. A star is transposed over 2. Okay, so this matrix is symmetric and it's just, in other words, when you observe the matrix, the entry Ij, you just know also that the entry Ji has the same value because your matrix P is symmetric. Okay, so I have, well, as I mentioned, the expectation of A is the same as P, and it's the same true for the expectation of H. Okay, so you can think of A and H as random matrix, which are noisy but unbiased observation of P. Okay, so the question will be to try to recover some information from the average of A and H just by observing a single realization of A or H. Okay, so and we would like to be interested by estimating the case largest eigenvalue of P and try to compare them with the k largest eigenvalue of A or the case largest eigenvalue of H, and the same question for the eigenspaces. And the message that we convey in this talk is that it is much smarter, despite the fact that H is symmetric, exactly as P, so H is in some sense closer to P. It is much smarter to compare the spectrum of A rather, to study the spectrum of A rather than the spectrum of H. The spectrum of H is very far for a low value of D, which would be what is interesting here. For the lowest possible value of D, the spectrum of H is very far from the spectrum of P, whereas the spectrum of A will be close to the spectrum of P. Okay, so it's a kind of paradox, which is asymmetric. So in some cases, as I wrote, the spectrum of P is much less perturbed by a random asymmetric noise rather than by a random symmetric noise. Okay, if you think that A is asymmetric and H is symmetric.
Slava, could you put the definition of H again? I'm sorry.
Sure.
Sorry.
Here it is.
Okay, it's the symmetrized version. And
yeah. Okay.
Yeah, thank you.
Okay, so I'll state a theorem now. So for stating theorem, you have to put some notation. So I will give you this detection threshold, which essentially answers the kind of question, the first question I mentioned. Okay, so you define a kind of noise, the kind of variance of your matrix P. So P is an unknown matrix, and you define Qij to be n times the modulus of Pij squared. Okay, you could remove the n, but there is an n in the paper, so everything is scale invariant. There is an n here and an here, but you could remove all of them. But whatever. Okay, so let's skip to what is written. So Qij is n times the modulus of Pij squared. And rho is the operator norm. So this is the operator. So this is the operator norm. So this is the L2 to L2 norm of Q. Okay, and the detection threshold is just the maximum between two bounds, an important bound, which will be square root of rho over d and L over d. L is the maximum entry of P. of this unknown matrix. Okay, so this is a kind of L1 bound because you divide by D, and this is a kind of L2 bound because you divide by square root D, right? And L is not completely optimal, but for the sake of this talk, let's take this. L is just a maximal entry of P. For example, for the next quick problem, it's fine. You have just 5 marks, 5 stars. The number of marks is just a discrete set with 5 values, so that's fine. But in this other situation, you may want to have a better definition for L. Okay, let's stick to that. Okay, so theta is a kind of competition between something which decay in 1 over D and something which decays in 1 over square root D. So at the end, the L2 bound will always win. Okay, so you can think as just for this talk that theta is essentially square root of rho over D. Okay, so now you order the eigenvalues of P. So they are real because P is symmetric. So the first one in absolute value, I call it mu1, and the last one, the smallest one, mu(n). P is symmetric, so there is an orthonormal basis of eigenvectors, and this is this spectral incoherence assumption. You assume that your eigenvectors, so they are unit norm, L2 norm, so the L2 norm is 1, but you assume that the L infinity norm is of order 1 over square root n up to some factor b. B could depend on n. Okay, so this measure how flat your eigenvector is. Okay, so for example, if phi is just the constant vector, to make it unit, you take phi, which is 1 over square root n. All entries are equal to 1 over square root n, and then you take b equal to 1. Okay, if you take a uniform point on the units on the n-dimensional sphere, with high probability, you will be able to make b like a square root of log n. Okay, a uniform point on the sphere is quite flat, and you can take b over the square root of log n. Okay, so b in your mind should be like something like n power little over 1. And we will work with a parameter which is, we'll assume that the rank is not too large, and we can relax this assumption on small ranks, but what is called the stable numerical rank in computational mathematics, which is just the sum of the squares of the eigenvalues divided by the largest one. Okay, so this is the largest, this is an upper bound on the rank of P. This is upper bounded by the rank, the algebraic rank. And so I will assume to make this statement which is correct, I will assume that all these numbers, R0 is a number of eigenvalues which are above this detection threshold. All numbers are like log n, or polylog, or at least n power little over 1. Okay? But if you look in the paper, there is a kind of quantitative statement. Okay, so just recall the assumptions. And the theorem is the following, that with high probability, all eigenvalues of A, so A is my asymmetric observed matrix, which are above the threshold theta, they have an eigenvalue, lambda k, which is close to the corresponding case largest eigenvalue of P. And all the other one, they are bounded by theta, up to little over 1 corrections. Okay? Let's see that in the picture. So P has rank 3. I take phi k to be uniform points on the sphere. Okay, so there are 3 eigenvalues. Phi 1, phi 2, phi 3 are 3 orthonormal vectors, which are taken uniform on the sphere, an n-dimensional sphere of dimension 2000. And so here D is equal to 5, and you see that the detection ratio is in square root rho over D is in orange, and you see that there is one outlier eigenvalue at 3, which corresponds to this one, and the two other one, 2 and 1, which are the two other eigenvalues of P, they are just completely disappeared in the bulk of eigenvalues in this mess. Okay. And you see that the statement looks quite sharp because there are some eigenvalues which are very close to this orange disk circle. Okay, if you increase D to be 10, so that you see that the eigenvalue 2 pops out. Okay, so the theorem looks correct, at least in simulation. You can also estimate eigenvectors, so I will try to be not too technical. So if you write P as a sum of its orthonormal as a diagonal operator in a well-chosen orthonormal basis, and you assume that the eigenvalues are well separated in some quantitative sense. And if this is true, if you call psi k the unit eigenvector associated to the case eigenvalue of A, okay, so phi k is a unit eigenvector associated to the case eigenvalue of P, there exists a gamma k such that the scalar product between psi k and phi k is close to gamma k, okay? And this will be true for all k between 1 and R0. Okay, so there is an explicit expression for this gamma k, okay, which is gamma k. So there is an explicit expression which is kind of ugly, but I wanted to show it to you. So which depends on the gamma k. You see, it's like you take the scalar gamma k is gamma kl is like a Gram matrix when you take it's kind of scalar product with respect to some weights which depends on this noise matrix Q. Remember that Q is just a matrix whose entries are the squares of the matrix P. Okay, so this matrix, so the scalar product is non-trivial, and it is given by an explicit formula, and you can think of that as being a scalar product with respect to some in a weighted when you weight your Euclidean space. And if you take two different eigenvalues, let's say mu k and mu l, and you take the corresponding eigenvectors of A, the scalar product is not vanishing, and you can compute the expression again against using this matrix gamma. Okay. If you take the rank 1 projection, the formula is easy. So pi is phi star. Okay, so it's just a rank 1 projection. Phi is a unit vector. Theta, the detection threshold, is simply the proportional to the L4 norm of phi. Okay, and the gamma, which is a scalar product between the corresponding eigenvalue of A and the corresponding and phi, it will be like 1 minus this ratio between the L4 norm of phi. Okay. And I will show you simulation, I think, later. And it's possible to be smarter than that because if you remember, A is not symmetric. So it has a left and right eigenvector, which are different. You can compute their eigenvectors, so I call them psi prime and psi. You can compute their scalar products. And it is again, you can express this again in terms of these gammas. And what is a smarter estimator is to, for the case largest eigenvalue, is just to take the average of the case of the left and right eigenvector of A, and you get an estimator of the case eigenvector of P, which is better by essentially a factor of square root 2. Okay, and here is some simulation. So here is this rank 1 simulation where N is 6,000. So D, you see D here, you have these plots of the, so the green one, the light green one is when you take the average between left and right eigenvector, and you see it's very close to theory. What you see in practice is very close to theory. This is just when you take the average with the right or the left eigenvector. And this is what you get when you take the symmetric matrix H. Okay, I did not show a simulation of the eigenvalue of symmetric matrix H, but the spectrum of H is polluted by rows where you have discovered too many entries, and you see that the scalar product performs very poorly for small values of D. Okay, so as I said, it's much smarter to look at the spectrum of the asymmetric random matrix instead of looking at the symmetric random matrix if you want to estimate P. Okay, how much time do I have? Okay. Now I will tell you that it's possible to make an improvement, okay, by increasing the dimension of the matrix. Okay, so this is improvement. So what I want to say here is just that the detection threshold was like square root of rho over D, but you can improve by the factor D. You can take it to be 2D, so you have an improvement of 1 over square root D, 1 over square root 2, because it's possible, and because what you have not taken into into account when you consider your asymmetric matrix A. You have not taken into account the fact that P is symmetric. Okay, so instead of having D observed entries per row, you have 2D observed entries per row. Okay, because you have to look at the observed entries on the ith row and the observed entries on the ith column. It's 2D almost. Okay, so for that, one way to use this information in a kind of efficient way from a computational point of view is to define a new matrix, which is called the non-backtracking matrix. You can define it as follows. You look at the set of pairs of entries which have been observed. Okay, so this is a pair of ij, such as ij or ji is observed. Okay, so the set of this set is the cardinal, the number of elements here is like 2dn, but it's a law of large number. And the non-symmetric matrix, the non-backtracking matrix, is a matrix which is indexed by this by this set of pairs. Okay, and when you do, you put a 1 between, you put a non-zero entries between the pair ij and kl. So this is I described what is the value of an entry of this matrix B. Okay, if the endpoint so E is ij, if the endpoint of E is a starting point of F, but F is not the reverse of E, but L is different from E. So this is this constraint. This constraint is explained here. And then once you have this constraint, but this is non-backtracking, you just put the value, for example, of the value of PKL, which you have observed, and you renormalize so that you have an unbiased estimator. Okay, and modulo some technical statement. All the results I mentioned for the asymmetric matrix A are true for the matrix B, but with D replaced by 2D. So it's more efficient in terms of estimation, but it's more costly from a computational point of view because the size of the matrix, instead of being n times n, is essentially 2dn times 2dn. Okay, so here I have some numerics for the same example of the rank 1 projection on the random direction of the sphere. And you see that the orange curve fits quite largely the other curve. Okay. What I would like to explain you is where this detection threshold comes from, and particularly where this square root of rho over d comes from. You have in this conference, there is a lot of people working on branching processes. So the reason is related to a branching process, and it's related to a famous paper by Kestel and Stigem from the 60s that you probably know. So that's what I will explain you, try to tell you why this threshold of square root of rho over d is related to the work of Kestel and Stigem on what is it called? Multi-type Galton-Watson processes. Okay, so what we will do first is to build an infinite tree, which will be n-ary. So every vertex will have n of springs. Okay. So, and I index that. So I take J0 to be a fixed number between 1 and n, and I take V, the set of which will be my vertex set of my n-ary tree, will be the set of finite integer sequence in n, which starts with J0. So an element of the case generation, you can write it as J0, G1 up to Jk, where Jk are in between 1 and n. Okay, so now from your matrix P, you can consider, you can define an operator on this infinite vector space L2 of V, okay, which is just by, you put entry, if you write this as an infinite, you see that as an infinite matrix, P as an infinite matrix indexed by elements of your vertices. So you will put all entries will be 0, okay, except when if U is of the form, if U ends with JK and U and UJ is an offspring, is a J offspring of U, you will put the entry between U and UJ, which will be just JKJ. Okay, where this is this is my original matrix, and this curly P is my matrix living on my infinite array living on the set of finite integer sequence. Okay, so this gives me a non-symmetric bounded operator on my infinite NRA tree. Now you can lift, so you can think of that as a lift of your matrix P on a larger space V. You can also lift the eigenvectors. If phi is an eigenvector, if p phi is mu phi, then if you define now, so phi is a vector in Rn, okay? Phi, capital phi is a vector indexed by V, such that the entry of phi of an entry J0 Jk is just the value of phi of small phi at Jk. So you just take the n vertex. What you realize that P of capital phi is equal to mu capital phi. So phi satisfies the eigenvector equation for my for my infinite matrix. But beware that phi is not in L2 of V. Okay, so you can think of that phi is a wave. Okay, so its phi is not in L2 of V. But nevertheless, it's an infinite. It's a vector. It's an infinite vector. It's a vector indexed by V, which satisfies the eigenvalue equation. So let's call that an eigenwave. Okay, now I will add some randomness. So what I do is to keep each edge of my NRA tree with probability D over n, and I obtain a Galton-Watson tree with binomial of parameter n D over n of spring distribution. And I make the same thing, and I make the same operator. My operator will become an operator which I've removed some edges, so my operator, I obtain a new operator which I call P percolation, and I rescale it to obtain a so I rescale it to have an infinite matrix A, which satisfies expectation of A is equal to P. So curly A is an unbiased observation of curly P. Okay. So this matrix is a kind of proxy for the matrix for the model I'm interested in. Okay, so what I do is if you take you remember I had an eigenvalue, I had an eigenwave of my infinite matrix P. I can define a candidate eigenvector for my random operator A, which is this, sorry, I'm very bad with that. Okay, which is, you can define it like that. So this is the expectation of this vector is again my vector. I started with capital phi, and this is if you see that in time, this is a discrete martingale for the filtration associated to the successive generation of the tree. And you can see when you can compute the bracket of this martingale. It's just a master exercise. And you see, when you compute this martingale, you will see this matrix Q, which appears naturally. And you will deduce that your martingale converge almost surely, and in L2, as soon as the Kesten-Stigem bound is met, which is this, the Kesten-Stigem bound will be this square root of rho over T. As soon as the eigenvalue is large enough, and large enough in the square root of rho over T, your martingale will converge. And when your martingale will converge, since your vector psi t satisfies this eigenvector equation in the shift, since psi t converge, you will obtain a random eigenwave, which is a random eigenwave. Okay, so this is possible as soon as you are above this Kesten-Stigem, and this is where this Kesten-Stigem threshold, and this is where my detection threshold comes from. Okay, so this is a kind of easy analysis, but now you have to come back to finite dimension. But keeping in mind what I told you, you guess that you have a candidate for something which will be a candidate eigenvector and a candidate right eigenvector. And so what you try to do is to decompose your matrix in terms of candidate left and candidate right eigenvector up to some remaining terms. And then you have to do some analysis, which I will, which goes in, so you have to compute the inner products between these candidate left and right eigenvectors. You have to show that the associated Kram matrix is well conditioned. And very importantly, you have to show that this is the operator norm of this remainder is small. And you use some spectral perturbation theorem. So this kind of strategy has already been used in a previous paper with Marc Lelarge and Massonnier. But here it's much more complicated because the crowd matrix is, this step is very different. And okay, so it requires some new analysis and ideas. Okay, so okay, so I'm out of my time. So.
Yeah, we.
Okay, so it's possible to do the same thing with rectangular matrix. Mm-hmm. So I just can give you a picture. So so this is a rectangular matrix of size 2000 by 3000, and so it's you take P, which is U times V star, where U and V are just standard ID vectors, Gaussian vectors. So this is a subsample of my true matrix. What you get when you consider the singular value distribution, which is what people teach to do in statistics course, and what you get when you look at my corresponding asymmetric analysis and an improvement thanks to using these non-backtracking IDs. Okay, so it's kind of convincing, I guess. Okay, so thank you for your attention. So there is a lot of work going on nowadays on these ideas of using non-symmetry. And thank you.